Assalamualaikum, my name is Danial Ikmal bin Rusman. I'm going to present my final year project about simulation of three-dimensional drilling using end colony optimization. So, background study. First, drilling has become a very important process in industry. Second, this transition has been possible due to technology advancement in drilling. Third, efficiency and production of drilling process can be increased by doing optimizations of drilling. Next, study focus on the searching of optimal tool path length with developments of end colony optimization. Problem statement. Mastercam is not focusing on minimizing the tool path length. Next, Mastercam generated tool path by optimizing parameters such as cutting speed, feed rate, and drilling diameter. Tool path length can lead to the reduction in machining time. Next, the result of tool path length on end colony optimization will be compared with Mastercam. Objective. The objective of this research. First, to simulate the three-dimensional drilling process using end colony optimization. Next, to determine the best parameter of end colony optimization in drilling process. Last is to compare the tool path length of simulations in drilling process using end colony optimization and Mastercam. Scope of study. The scope of this research are MATLAB software will be used to develop end colony optimization algorithm. Next, the process that involve in drilling three-dimensional by using Mastercam software and end colony optimization. Next, the research is about comparing the result of tool path length using Mastercam and end colony optimization method. Next is literature review, optimization tools and technique. It's cover conventional techniques and non-conventional techniques. So, conventional technique has a Taguchi method based, factorial design based, and RSM based, while non-conventional cover genetic algorithm, simulated annealing, and taboo search. The optimizations of drilling process using conventional method. First, Sumesh and Melvin is using Taguchi method. Second is Yogandra using a Taguchi method. Next is Nisha Tamta, which using Taguchi method. And next is Amran using response surface design methodology, RSM based. Last is Varata Julu is using response surface design methodology, RSM based, and Taguchi method. While for the optimizations of drilling process using conventional method, there are 5 methods. First, end colony optimization by Nari. Next, using end colony optimization ACO by Eldos. Next is particle swarm optimization by Adam. Next is Kaku search algorithm by Lim. Lastly is Firefly algorithm by Ismail. Next is end colony optimization. It consists of 4 steps. First, and choose a path among others and lay a pheromone trail on it. Second, all the ends are travel some path laying off a trail proportional to the quality of the solution. Next, the edge of the best path is more reinforced than the others. Lastly, the evaporation ensures that the bad solution disappears. There are few equations that will be used in this study. First, equations of probability of end colony optimization. Next, the equation of pheromone trail updating rule. Lastly, equations of the amounts of pheromone deposited by N. Next, the methodology in this study. First, it starts with a literature review. Next, design a workpiece. Next is determine the X, Y, and Z coordinates of the hole, followed with simulations of ACO in MATLAB and Mastercam, and determine the minimum tool path length between these two methods, and determine the machining time between these two methods, and compare the result between these two methods. By this result, we will be analyze the result and end the discussions. Workpiece that are used for the simulation. There are two workpiece: simple workpiece design with 10 holes and complex workpiece design with 154 holes. Developments of finesse function based on n colony optimization. It is to find the cutting tool travel path distance between two nodes depends on the plane where two nodes belong and to be calculated using the equation stated. Developments of n colony optimization ACO using MATLAB. Based on the flowchart, it starts with coordinates of the hole, followed with define the perimeter of ACO, and calculate the finesse function, which is tool path length, followed with pheromone trail updating, and it will display the tool path distance, and it will end the MATLAB simulations. While methodology in MasterCam, it starts by design the workpiece, and next it's going to define the machining method, where in this study we are using cross-sort method, and thus it will select the machining surface and moving to define the machining parameter such as the feed rate, cutting speed, and so on. Next, we're going to define the coordinates of the holes, and thus it's going to modify the path, and if yes, it's going to go to verify the path, and if not, it's going back to the define machining method. And next, we set the program, and thus moving to the modified of the program. If yes, it's going to show the output of the shortest path length of the simulation. If not, it's going to modify the path. Comparison of tool path length. Between ACO and MasterCam, the simulation will be compared with the equation stated. Result and discussion. Based on the objective to find the best parameter, the parameter that has been picked are number of iteration, weight of pheromone, weight of trail, and evaporation coefficient. The first parameter, number of iteration. The study of number of iterations start with 100 to 900, with the weight of pheromone at 5, weight of trail at 4, number of N at 10, because of simple workpiece design that I use. And from this result, it shows that number of 900 iteration have the best tool path length at 286.9650 mm. Next, the parameter that we also pick is weight of alpha and beta. As we can see from the table, we are producing 25 samples and with different weight of pheromone. And it's clearly shown that the shortest tool path length is obtained from the sample 24, which is the weight of pheromone are 5 and weight of trail are 4. And this is the shortest relative to the other parameter at 6770.9860 mm. So, next parameter that we are studying are the evaporation coefficient. The evaporation coefficient range that we use are from 0.1 to 0.5. And the weight of pheromone, weight of trail, and number of N are constant. This study showed that the best tool path lengths are at evaporation coefficient 0.4, which is 6894.2709. After all the parameter that has been found, the best tool path length for simple block design workpiece are 286.965 mm, with iteration at 900, weight of pheromone at 5, weight of trail at 4, evaporation coefficient at 0.4, and number of M at 10. While for complex block design workpiece, the best toolpath are 6770.9860 mm with the same best parameter at 900 iteration, weight of pheromone at 5, weight of trail at 4, evaporation coefficient at 0.4, and number of N at 154. Result on toolpath length on Mastercam. For simple block design workpiece, the number of samples are 16 based on the sorting method, which is cross sort, and it shows that result from sample 5 to 8 showing the same result, which is the best toolpath for simple block design workpiece. For complex block design, it shows that the toolpath is a bit crowded and going far from the nearest neighbor. The best toolpath is from Z- counterclockwise at 55,828.0.9050 mm. So, moving to the comparison of ant colony optimization with Mastercam. This is to answer our third objective, comparing ACO and Mastercam. So, for simple block design workpiece, it can see clearly that ACO is moving to find the shortest toolpath length, while Mastercam is moving on the directions that are higher in the numbers of toolpath length, which take a longer distance. And for Mastercam, the design for this design, the minimum toolpath length is 569.878 mm, while ACO at 286.9650 mm, and these two designs are compared in the equations shows, and the reductions of toolpath length that we can see is 49.64% reductions of toolpath length between these two methods. While moving to compare for the complex block design workpiece. For complex block design workpiece, ACO generate 6,774.9860 mm, while Mastercam generate 55,828.9050 mm. We can see clearly that the Mastercam toolpath is quite crowded, while ACO toolpath is less crowded, and Mastercam is moving in the directions where not choosing the closest toolpath, while ACO is going to the closest and finding the best toolpath for the complex block design. And these two results are calculated to find the percentage difference, thus ACO producing a reduction of toolpath length at 87.87%. To conclude this study, we already answered three main objectives of this study. The first objective is running a simulation in three-dimensional. Based on the workpiece, it shows that the simulation are run through X, Y, and Z axis. Next is to find the best parameter for ACO. And we find out that the best parameter are at 900 iteration, weight of pheromone at 5, weight of trail at 4, and evaporation coefficient at 0.4. And lastly, comparison between ant colony optimization and Mastercam of the toolpath, and it shows that for simple block design workpiece, the results show a reduction of ACO toolpath at 49.64%, while for complex workpiece design at 87.87%. So the sustainability element in this study, there's a lot of advantage in this study where it can reduce the machining time, reduce the cost, increase the productivity, and increase the profit in the industries.